Hi everyone, my name is Mohammad Kamil from School of Mathematics and Computer Science, Institute of Business Administration, Karachi, Pakistan. Today I will be presenting our research titled Hybrid Semantic Web Architecture for Context-Aware Agricultural Decision Support. In this work, we address major challenges faced by farmers in making informed decisions. And we propose a hybrid system that combines semantic web technologies with a modern MERN-based application. Let's begin by looking at the motivation behind this research. Agriculture is a major part of economy, especially in Pakistan where it employs a large portion of the workforce. Despite this, farmers still rely heavily on intuition and the previous season's performance. There are major gaps in access to timely expert information, and current digital tools mostly support record keeping rather than real decision making. This highlights the need for a system that can guide farmers with accurate, context aware recommendations. Research gap. Existing systems typically use either machine learning or ontologies alone, and both approaches have limitations. Most cannot handle variations in soil, climate, and growth stages. They also don't combine human expert knowledge with automated reasoning. Additionally, collaboration among stakeholders like agronomists, fertilizer companies, and government departments is limited. Objectives and questions. The main objective was to build a recommendation system that uses semantic technologies to provide situation-based advice. We also wanted to integrate expert knowledge dynamically and ensure the system remains scalable for different stakeholder groups. The research questions focus on utilizing spatiotemporal data effectively, identifying the advantages of a semantic web and MERN combination, and understanding how the hybrid model improves decision making. A system overview. The system integrates a semantic web reasoning engine with a modern MERN application. It includes a modern It basically includes more than 25 expert validated rules for fertilizers and pest management. When a farmer submits a query, the system first applies semantic reasoning. If the reasoning engine cannot answer, the query is redirected to human experts. Their responses improve the system over time, making it smarter and more capable. So this is the diagram how the system looks like. Okay, so architecture. The platform is built using a three-tier architecture. The front end is developed with React and Material UI, providing a responsive interface for farmers and experts. The middle layer uses Node and Express along with OWL ontologies and SQL queries. The data tier uses MongoDB, which stores stakeholders' data and integrates with the semantic reasoning outcome. Together, these technologies provide scalability and fast responses. So this is the architecture diagram. Then we have system workflow. Here we see how the entire process flows. Farmers submit queries, the semantic rules try to generate a recommendation, and if the system cannot answer, the query is passed to experts. Once experts reply, their answers are incorporated into the knowledge base. This means the system gradually reduces its dependent its dependence on manual expert intervention over time. So this is the system workflow diagram. Then we have ontology and semantic model. The ontology represents structured knowledge about crops, soil types, fertilizer categories, diseases, and pesticides. It defines clear relationship among these elements, enabling reasoning. This model was built using OWL and validated by agricultural experts to ensure real-world accuracy. The ontology allows the use system to understand and interpret farmer queries in a meaningful way. This is the diagram of ontology and semantic model. So, inference rules. The inference rules from the backbone of automated recommendations. For example, certain fertilizers are recommended for what depending on whether it is in the germination or maturation stage. Soil-specific rules also adjust recommendations based on nutrient levels. Pest management rules provide targeted pesticide suggestions based on the disease detected in each crop. These rules combine expert knowledge with semantic reasoning. Then we have two-tier query resolution. In this, the two-tier model is a major contribution. The first tier semantic reasoning provides instant automated answers. The second tier ensures that complex or unfamiliar queries are handled by experts. Each expert response expands the system's reasoning ability. Over time, the need for expert intervention decreases, making the system more efficient and self-sustaining. Then implementation and testing. The system was implemented using the MERN stack to ensure performance and scalability. Multiple testing phases were conducted: interface testing, authentication tests, recommendation validation, and integration checks. For expert responses, different stakeholders, such as farmers and agricultural advisors, have separate interfaces tailored to their needs. Results. The system successfully produces accurate recommendations for four major crops: wheat, rice, cotton, and sugarcane. It handles fertilizer optimization and pest management effectively based on soil type, disease, and growth stage. The hybrid model performed well in real query scenarios. The integration of semantic web and MERN technologies proved to be adaptable and scalable. Limitations. The system is currently focused on Pakistan agricultural conditions and only supports four crops. Its accuracy also depends on expert availability for complex queries, especially when new diseases or combinations sorry, unfamiliar combinations occur. Another limitation is the lack of real-time sensor data from fields, which would make recommendations even more dynamic. At the end, conclusion and future work. To conclude, the research demonstrates that combining semantic web technologies with a modern web stack creates an effective decision support system. It bridges the gap between automated reasoning and human expertise. Future plans include building a mobile app, expanding the ontology to more crops, incorporating IoT sensors for real-time data, and collaborating with government agencies to scale the system nationally. So that is it. Thank you.